All right, good morning, everybody. So I graded the bonus test. It benefited just about all of you that took it, at least to some degree. Went better for some than for others. I'm going to briefly go over its solutions. So some key ideas to bear in mind about how this went. So the first three questions were all problems we had done in class. And so kind of what I was looking for there was determining how well had you assimilated what we had done in terms of being able to reproduce those results. The fourth problem, the insert before, was something I had mentioned at the end of one of our classes as something that might be worth practicing. And then the fifth one, insert in order, was kind of a test of how well could you put together some different ideas that we had explored in order to demonstrate real mastery of these ideas. So if you got most of them, mostly you're all right, you should feel great about where you're at. If you fell short, you should probably think about why that's the case. What concepts are still obscure. In my observation, people were still a little uncomfortable with constructors, with understanding the relationships between different data types. So, for example, you can't assign next to be a value because next is a node and value is a string. Some of you are still struggling with that idea. That was fairly clear from the test. And so if those are ideas you're struggling with, you're going to need to work on that stuff. Do some more practice problems. Come visit with me. I'll be happy to go over your tests with you individually, as the case might suggest. I did want to go ahead and walk through the two that we hadn't done before. So here is insert before. So one really common thing that I saw was attempts to reason in terms of the next node when it really wasn't appropriate for the problem. So when we think about something like insert before, we want to be examining the value from this node, the current node, and then perform the insertion by taking advantage of this return value as representing the new start of the list. So all you have to do is use the constructor to allocate a new node with the value to insert and this itself as the next. And so by doing that, you've effectively rebuilt the list. And several of you got that, but it was far from universal. Something else that I saw that was actually correct, but sort of more work than necessary, was instead of putting this here to create a new node with value and next as its values. That turns out to be completely correct, but it wasn't necessary to allocate the additional node. So in any event, if you found the target value, you create a new node with the value to insert and this as the next. Why does that work? It's because we're inserting before. We're inserting before. If next, then otherwise, if next isn't null, we update next to be next.insert before, and the result of that recursive call. Again, the idea is insert before always returns the node that is the new start of the list. More often than not, it's just the old start of the list. And that's why we've got return this right down here. Any questions on insert before? So then insert in order, like I mentioned, I added as kind of an extra challenge to see how well you could put together some of the ideas we've been exploring. If you look at it, you can kind of see, it's really an awful lot like insert before, as if it were no accident, in fact. Big idea, though, that you had to apply here was the idea of a comparator that we went over in the lab on Tuesday. So when inserting before, we're not looking for a target value. Instead, what we're checking for is to see if the value at the current node is bigger than the thing we're trying to insert, then the thing we're trying to insert ought to go before it. And so we return a new node, value to insert this. In other words, it's exactly the same insertion technique that we use over here. A big difference, though, is if we're inserting an order and it just happens to be going all the way to the end, we do have to go ahead and put it in place, right? So if next is null, we make next a new node with value to insert and null. Otherwise, it's a very similar recursive call. And in this case, once we have figured out what we're doing, we just return this as the new start of that same list. And something that's kind of cool about this is that if you use insert in order, you have a linked list that is always guaranteed to be sorted at all times. And being sorted is a really useful and interesting property that we're going to explore quite a lot over the next few weeks. Cool. Any questions about that? Okay, I have also updated our course schedule. Let me familiarize you with the way things are going to proceed. My original plan was not to run a lab during the week of fall break. However, having had to push back on the lab in order to create enough space to get lab 4 finished, we are going to go ahead and have lab next Tuesday. And so lab 7 is due Monday. And then on this coming Tuesday, we're going to go back and do lab 6. They don't actually depend on each other. So it'll work. We'll make it work. But yeah, so lab 6, we're going to do the Tuesday of fall break week. So this coming Tuesday. And that's part of how we're going to get caught up. I've redone some of the deadlines on projects 2 through 5, and this updated schedule should work if we manage to not get further behind. So that's the plan going forward there. Any questions? Just looking ahead, project 2 depends heavily on lab 6. So on that Tuesday, the 15th, I'm going to go over both lab 6 and I'm going to explain project 2. And project 2 will be due 10 days after lab 6. And from there, I think we'll be able to get caught back up. Once we come back from fall break, we're going to do a lab on sorting, and we're going to keep moving from there. Any questions? All right, we are going to now spend some quality time thinking more about heaps and thinking about how they work, how they're put together, and importantly, how we understand their efficiency. So let's review. Would somebody like, so we've got the following main operations, right? We've got the idea of peek, the idea of add, and the idea of remove. So somebody remind me how peek works in a heap. It does. And how does it know where the highest value is? And how does it know where the top of the heap is? And how does it know what index it is? Right. It's the top of the heap is always at index 0. Silly pen. All right, there we go. Top of the heap is always at index 0. So that's pretty straightforward. It's easy to implement. It, of course, depends on these two working correctly. If either of these has a bug, this fails, right? So the way that we think about this a little more formally is to say that both add and remove, let's go on with this thing. There we go. Both need to implement the heap property. So what is the heap property? Anybody remember? What is it that makes an array a heap? They do have parent values and left and right values, and that's very, very important. What is the relationship between those values? Right, so the heap property is that you have a parent value that's greater than the left and the right child values. Technically, we're perfectly happy if it's greater than or equal to. And as we saw in the lab, as long as we're internally consistent, we can even create a min heap and require them to be less than or equal to. Both min heaps and max heaps have their uses. They're both quite valuable as data structures. So that's the heap property. It has to be maintained when we add and when we remove. So the overall strategies then, with both adding and removing, is that we do a simple operation to add or remove, and then we check to see, did we violate the heap property? And if we did, we repair the heap so as to restore that property. So let's review add. So when I'm thinking about adding to a heap, what I do is add to the end of the array. And now I need to repair any violations of the heap property. So thinking about this as a max heap, how do I check for violations of the heap property? How do I check? I'm definitely using .compare to. Yes, that is absolutely the case. What are the things I am comparing? Off your phone, Morgan. What are the things I am comparing? I am comparing the parent and the child, right? So I need to compare parent versus child. And then if they're out of order, I will swap and then keep going. And if they're in order, then my heap property is in place and I don't need to keep going. Now here's where this gets really fascinating, is trying to figure out, at worst, how many of these swaps must we perform? Or maybe phrased a little more helpfully, how many times must we do a comparison? How many times must we do a comparison is going to be the way that we reason about the efficiency of this. In general, whenever we think about efficiency, it's always in terms of counting an operation. It has to be one operation that we count. If we feel deeply compelled to count more than one operation, I mean, there's nothing stopping us from doing that. Lightning bolts are not going to come down from the heavens, but we do need to count them separately from each other. We need to do this chain of reasoning 2 independent times in order to understand what's happening. With a heap, there are important traditional reasons why the operation that we count is going to be the comparison. And what's the nature of that reason? We'll get to this probably on Monday, maybe today, depending on how things go. A really cool thing you can do with a heap is use a heap to sort an array. So heaps themselves wind up being the core of a really powerful sorting algorithm. Sorting algorithms in general are compared in their efficiency based on comparisons. How many comparisons do they perform? And so to reason properly about a heap in that overall context, we need to think about how many comparisons is it performing. So We're going to think about this a bit informally first, then we're going to formalize this a little bit more. So the way we're going to think about it informally is to run through an example and see if we can develop some intuition about how we might think about this, because it's actually fairly subtle. But once you master this little bit of reasoning, you're going to find that it's applicable for a lot of different algorithms. So without further ado, I am starting my max heap with the number 2 at the top. And now I am going to add to my heap the number 7. What's going to happen? Yep, I'm going to need to swap. And of course here, I am upending the entire heap because the heap is very tiny and has only 2 elements. Now I'm going to throw in a 5. Do we have to do anything? Nah. Now I'm going to put in a 1 because I'm still not wanting to do anything. But now I'm going to put in a 10. So what needs to happen? 2 and 10 need to switch. And so I'm going to switch them. And now what happens? Bless you. 10 and 7 need to switch. Good. So 7 goes there, and 10 goes there. What parts of the heap were untouched?
5 and 1.
5 and 1 were untouched. We're still hitting the heap, but we were able to ignore some. So now we're going to throw in a few more. Let's put in a 4, bless you, and a 13. So when I put in the 4, what happens? Nothing. It was perfectly good. What about the 13? What's that, Caleb? It's going to need to switch with 5. And then it'll need to switch with 10. I'm just going to fill my 10 in there. And then my 13 goes up here. Now, the only elements that were affected were these. So this is starting to get a little more interesting. Notice that we've now transitioned from a majority of the elements were affected to a minority of the elements were affected. We went from more than half to less than half. And we're not going to stop here. So we're going to throw in a few more values. Although that, I mean, I had to highlight the circle, but now it's kind of ugly, so I'm going to get rid of it. And oh, wow, that was remarkably non-destructive. Okay. Mostly, except for that. Okay. So I'm going to put a 9 into my heap, and now what will happen? Yeah, it's going to, the 1 and 7 are going to move down, and the 9 is going to go up here. And now I'm going to put a 6 in my heap, and that's just going to go down there. And you know what? Now I'm just going to put a whole other 1 in my heap, and then even another 1 because I just don't feel like doing a lot of swapping at the moment. And I'm getting a little crowded, but we'll survive. I'm going to put a 17 in my heap down here. And so, as we know, what will have to happen is the 17 and the 4 are going to trade places. And then the 17 and the 10 are going to trade places. And then the 17 and the 13 are going to trade places. Now notice that the unaffected part of my heap is getting larger and larger relative to the total size of the heap. In fact, at this point, I would be content to say that when I do a heap repair, I'm actually skipping most of the heap. So this is a pretty powerful idea. Clearly, in some way, the number of comparisons I have to perform does depend on the number of elements in the heap. But I'm not doing work for all of them, just kind of a fraction. of them. In terms of the, this is actually kind of a jumbled mess at this point, but in terms of the overall layout of this data structure, what are some ways you can imagine to talk about its physical layout? What are some ways to quantify its physical layout? Thoughts?
Tree.
Okay, what does tree even mean, Morgan?
It's a tree. It's almost like a family tree.
It is a lot like a family tree. That's a great analogy. Let's see where this takes us, right? If we think of this as being like a family tree, what are some different aspects we can quantify? Yeah, Kate. There are paths, and we can think of these paths as saying something like, how many family generations are there?
Yeah, right.
And this is a really fascinating way to think about it. We've got both the number of elements, what I'm going to informally call the number of generations in the family, what I'm going to somewhat more formally call the height of the tree. How tall is the tree? What's the distance from the root to the end? And I think what we've seen in these examples is that, I'm going to write this down, the number of comparisons for a fix-up on an add is less than or equal to the height of the heap. So the number of comparisons we have to perform is going to be less than or equal to the height of the heap. So this is a really valuable observation. If we can calculate the height of the heap, we can know an upper bound on the number of comparisons we have to perform. On one level, this is a great advance. This is great progress. We've got a conceptual framework for thinking about this. On the other hand, it looks like we've just passed the buck. In other words, well, what is the height? Of course, we're not going to waste any time. We're going to calculate it. So let's think about the height of the heap. So let's say our heap has, come on, Penn, you can do this, n items. It has n items. We need to figure out the height. It's a little tricky. We've got n items, and we're wondering, what is the relationship between n and the height? What are some constraints on this relationship, just to start with? Right. We know that n is in some way greater than or equal to the height. So it's a valuable starting constraint. But I would say we can do a little better than this, actually. So I'm going to draw maybe a slightly prettier little pyramid here and see what kind of insight we can get. So all right, so what's n in my little example here? Yeah, I have 7 items. What's my height? We would conventionally say the height is 2. That is, we think of the height as the number of hops that we need to get to the root. Again, this is a convention, but it's a helpful convention. It's a helpful convention. What it allows us to do is say something like, if I've just got one node, the height is 0. And by doing that, I can say the number of nodes is strictly greater than the height, which I think is conceptually useful. All right, well, we're going to add another level to this and see what happens. So if I add another level, I have H, I, J, K, L, M, N, O. So now N is 15, and my height has only gone up by 1, which is 3. So if we hand wave just a little bit, what we might say is that the effect of adding a level is that n equals n times 2, but height only equals height plus 1, right? We went from 7 to 15. We went from 2 to 3. So that's a really interesting relationship. Every time we add a level, n goes up by 2, but the height only goes up by 1. So what is kind of a mathematical tool for thinking about something getting multiplied by itself a bunch of times? An exponent. In other words, we could imagine taking n and multiplying it, right? Or wait, let me rephrase this. The number of nodes is going to be something. Oh, come on. Okay, one more time. Scribble, scribble, scribble. All right. 2 to the height. And so now what we really need, though, is to know this height. Why do we need to know the height rather than n? Well, it is easy to know n, but why do we care again about the height? Just quick. It's the number of comparisons, right? So if I want to know the number of comparisons, I have to solve for h. Now, here's kind of a funny little story. Right now, as I mentioned to some of you, my wife is teaching Algebra 2, okay, among other algebra-ish classes. And she sometimes encounters provocative questions like, why would I ever use a log for anything? How will this affect my life? Now, not all of these people are going to become computer scientists, but you all are, and it's now affecting your life. Right? See, we need to solve for the height. And here's a way that we can do that. We can take the log base 2 of both sides. We can, turn the eraser off and take the log base 2 of both sides. So, so far this just sort of looks like a loggy mess. Why did I throw a log in there? What does this do for us? Why am I left with h on the right side? What log property?
Logs. There's an exponent, pull that h out front. And then log 2 is 1.
Good. H is log 2n. Why is log 2 of 2 equal to 1? Because 2 to the first power equals 2. The log is just the inverse of the exponential. So this is a fascinating little result. When we repair the heap after doing an add, the total number of comparisons I need to repair the heap is log base 2 of n. Incidentally, if in your solution to the lab, and I know some of you did this, in your while loop on your repair, you just ask, is heap every time? Is that is heap call doing one comparison? How many comparisons is it doing? How many? Yeah, it's doing n comparisons, right? I had you write is heap to check if it's a heap. The reason I had you write is heap was actually to make the unit tests work. Is heap is not actually a method I would want you to use in a production context with a heap. So if you use is heap in your add fix-up or your remove fix-up, I would like you to see about replacing that with a comparison between a parent and a child. Okay. So that your heap is actually doing the proper number of comparisons. All right. So I'm going to look for that once you submit it. Okay. So for full credit, I'm going to expect that your add and remove fix-ups do the proper numbers of comparisons. So log base 2 of n. What a fascinating, fascinating function this is. What might I mean by fascinating? I'm going to write a little program here. Oops. So what I thought might be fun would be to put together a little program that shows us the relationship between n and log base 2 of n. To really add to the fun, I thought it would be cool for us to write our own function to calculate the log base 2 of n from scratch. It's actually pretty easy to do, and it will bring a lot of insight. So we're going to start by writing that. Public static int log 2 int n. Okay, so when I'm trying to think about the log base 2 of n, the way I can think about it is, how many times do I have to divide this by 2 in order to get down to 0? So to do that, I can have kind of a while loop. So I can have int count is equal to 0. We're going to do a while loop.
Okay, just making sure.
Yeah. The short answer is yes, it would also work, but the longer answer is how it works would not be altogether clear. So we're going to stick with the while loop. So while n is greater than 0, we're going to say n slash equals 2 and count plus equals 1. And then we're going to return count. We're going to want to test this, of course. So I'm going to, whoops. Where was my little, yeah, there we go, create test. So let's write some tests and make sure we got this correct. So at test, public, void test log. So let's pick some sort of obvious, nice, easy ones. So 1 should be what we get for logging dot log 2 of 2. Sound good? Yeah. And then if we do logging dot log 2 of 4, we ought to get a 2. And if we get a 3, it should have been from an 8. And then maybe we'll throw in kind of a fun test of a nice big number. So if we ask for the log of 65,536, that should be 16. Yeah. So this will be a useful start to see if in kind of the nice sane cases this works. So okay, so it failed, and it expected a 1, and it got a 2 with my 2. So let's see how that happened. N was 2, count was 0, so then n went down to 1, and count was 1. And then it came back up, and now n1 is greater than 0, so it 1 slash equaled 2, and then count went up to 2.
So Should we do it -1 maybe?
I mean, that would be one way. What might be another, though? Actually, this condition is wrong. It should be greater than 1 because anything to the 0 power is 1. So let's try this. Let's try this. Okay, it passed those tests. But we're not really going to stop there because those were sort of the fun, easy tests. Let's see what happens in a harder case, like this. What should be the log base 2 of 6 if we're dealing with integers? I think we still want it to be 2. We're going to truncate. We're going to round down. Let's see how we do. We passed. All right, so I'm starting to feel pretty good about this little log, right? So this function is really useful to visualize because if I were to guess, you all can contradict me if I'm wrong, but if I were to guess, most of the times in your life when you've calculated a logarithm, you have probably used a calculator. You probably have never calculated one by hand. Well, one or two of you might have. I don't know, in physics, do you ever calculate by hand?
Sometimes.
Sometimes?
Graph them a lot.
Yeah, you definitely graph them a lot. Okay. So I think it's pretty valuable to be able to visualize what the calculation is for a log. And that's the value of this function right here. There's nothing hidden. We know exactly what the calculation is. So now what we're going to do is write a little loop. We will start at 0. We're going to start at 1. We're going to go up to what height of a tree might be the biggest, or what number of nodes in a tree might be the biggest number of nodes that's interesting. All right, 1 billion is the winner. So that's 1,000. That's 1,000,000. That's 1 billion. I plus plus. Okay, this is a little psychotic. We're obviously not going to be able to view all of this output. So what we can do instead, well, you know, there are things we can do. We're going to create a variable called last log, and what we're going to do is only print it out when it changes. When we get a new log from a given value. Okay. So we'll say int log equals log base 2 of I. If log is not equal to last log, we will print out I, and then a comma, and its log, and then we'll say last log equals log. So this should give us some insight, right? Let's see how it does. So I hope you're kind of amused at the fact that it started fast and then it's kind of slowed down a bit. As if every time it prints something, it's going to take twice as long to print the next line. But what's really fun about this is looking at kind of this side-by-side comparison. So initially, in those examples that I was drawing, the log was relatively similar to the size, right? So with a size of 1, the log is 0, size of 2, it's 1, 4 is 2, 8 is 3. It's different, it's smaller, but it's not a big deal. But then we get down here, 1024, the log is only 10. And then we get all the way up here for 536 million items. The log is 29. Good answer. So I want you to think about how powerful the idea of a heap is in this context. I can put 500 million items in my heap, and when I do an add, it will fix it up with 29 comparisons. That's it. And every time I double it, it only needs one more comparison. So I, in fact, can put an insane, phone away, Morgan. I can put an insane amount of data into my heap, and to fix up an add is still extremely fast. Now, is this quite as fast as adding and removing from a stack or a queue? Well, no, right? With a stack or a queue, there was no dependency whatsoever on the number of items, right? But with a heap, there is a dependency, but it's a really weak dependency. Thought about it in an inverse way, log time for an algorithm is the inverse of exponential time. So if you imagine the other direction, like every time I added one item, I had to do this many comparisons, that would be an exponential time algorithm. Informally speaking, as computer scientists, if we encounter an algorithm that is exponential, we proceed to do something else. Like literally anything else. Like give up. But log, being the inverse of that,
Question, is there a log equation? Is there a log for this equation?
yeah, we just went over it.
No, I mean, is there like a log function built in the Java?
Oh, yeah.
Okay, because that was, I was just curious.
Yep. But for this case, I chose not to use it so that you all could see how a log actually gets calculated deep down. An integer log. Obviously, a floating point log would take more code than this.
Yeah,
In practice, it's actually implemented, even hardware log is implemented, or even floating point log is implemented in hardware as a practical matter.
wait, hardware meaning,
Circuits. Like,
I know, okay, 'cause, I'm sorry, this is what I remember from circuitry.
you probably didn't study how to calculate log in the circuits class.
Well, no, I didn't take circuits, I was just thinking
Yeah.
based on what I remember.
Yeah. So in any event, this log idea is a really powerful idea. If we can say that an algorithm is logarithmic in the size of its input, that's a pretty good sign that it's a good, efficient algorithm. You might wonder, how often do we get to make this claim? And there are two answers, both not that often and fairly often. Not that often in that you don't frequently have all that many algorithms where a single operation is log n time. You will find a lot of algorithms, and we're going to be hitting them repeatedly over the next couple of weeks, where log n is one of the factors in the calculation. And so understanding what it means for the log n to be a factor, that is, grows really slowly, is an important idea. This log base 2 is going to arise over and over and over again. And why is that? It's because log base 2 time comes when you can rule out half of the data on each comparison, which is what we did here. With the heap, we can rule out 1/2 of each level as we go up. And when you rule out a lot of halves, well, 1/2 to a very high power becomes a very tiny fraction. Like ultimately 29 over 500 million. So very powerful idea. Very powerful idea this is. So on Monday, we are going to examine, we're going to talk a little bit more about removing from the heap. And then we're going to examine how heaps can be used to sort an array very, very efficiently. And that'll be our first sorting algorithm. Depending on how Monday goes, on Wednesday, we will probably hit a second one. See you then.